Sunday. Okay, for video watchers, here's a little bit of a review, and remember that chemical potential with our stupid example of ice melting. Chemical potential is the most important thing in the world. It is, we're going to work in a constant temperature, constant pressure world. Even if partial pressure changes, as in the example I just gave, partial pressure of a particular A or B may change, and that does stuff, yes, but the total pressure did not change, and I pointed that out to you. And because of, simple examples, if a cat is $10, how does adding a cat change my pocketbook? Well, it changes it by $10. What? Huh? N, not T. Right. Yeah. Thank you. Yeah, my bad. I'm just kind of rolling off the top of my head. So, and so remember that this is the number of the table in the back of the book, and because of the first law, I'm able to do this. Now again, I'm going to be working at STP. Just to be friendly, I could work off that condition. Actually, I will do one example of that. But because of the relative nature of energies, the first law, I can use this for everything. But I just have to be consistent. So when I'm doing all these mixings and these reactings and all these things I could ever do with chemicals, as long as I consistently use formation G's for everything, I'm fine. Because that component of the bond making and breaking from elements in their standard state gets wiped out when I do the ultimate difference of before and after mixing. All those elements, reacting get wiped out. Anyway, so that's as clear as I can make it. Let's see, what else do I want to say? I guess that was about it. Again, for your homework, the fact that mixing is entirely entropically driven, because I'm dealing with perfect gases and they don't interact, so there's no reason to think that there's an enthalpy. Oh, here's another little factoid, and here, let me write this down. I'll write down the equation I just wrote down a second ago. nRT chi A, ALN chi A. There's another way that I know that this is pure entropic. This is a purely entropic thing, and that's that there's natural logs in it. It's not something plus a natural log, it's all a natural log. Natural logs are a clear indicator of entropy. So even in my own graduate research stuff, when I see an equation that describes energy and I see a natural log, that's the entropic contribution. Entropy naturally wants to show up as a natural log. So given that there's not like this is something plus a natural log, it's all a natural log technically because it multiplies. I know that this is pure entropy. And I just said that a minute ago. Now here's the trick about reacting. Right now I've done mixing, which is a necessary evil. All right, now I've done this part, now I'm going to do this part. Now here's the crazy thing about this, is that actually what you need to take into account is that when A and B form C, they're going to demix. And that's because if the reaction goes to completion and I've got all gas molecule C, it's not mixed with anything, it's by itself, and that would be bad. So A and B mix, we just covered that, it's good. We'll call that a negative delta G's, negative mix delta G, which we just covered, is good. It happens. As they react to form C, that's actually good because we're mixing more and more, but it stops. It comes to an end point and eventually starts to hurt the more and more C you get, because eventually as you form all C, you're actually in the process of demixing, which is bad, right? Good to mix initially, good to mix more when you make C, but eventually it turns bad because you're starting to demix once you get enough C and you're losing all your A and B. That's the executive summary. Now let me prove it. So, okay, now what do I want to do here? Okay, let me actually make this a little bit harder so that I can cover any type I'm going to make it a little harder so that I can cover any example that I actually throw at you. So I'm going to have A and B and C and D. And again, I will not give you hard examples on a test, especially on a test. But so if I give myself a generic albeit difficult example. Any reaction I actually give you will be, just like A goes to B, so it'll be easier than this. So anyway, okay. Now what I'm going to do is now that they're mixed, A and B are mixed, I'm going to let a little bit of a reaction go. So let's call this the extent of reaction. And so what does that mean? It's easy. Now, for a reaction to go, A is being consumed, B is being consumed, C is being created, and D is being created. And with this little symbology, what I can do is just point out that I can just say it's the stoichiometric coefficient times the extent of reaction. So I guess this is actually a good definition of extent of reaction. If this is 0, then A hasn't reacted. If this extent of reaction is 1, then I've gotten rid of all my A. It's all gone now, right? Because, I hope that's obvious. Anyway, that's the purpose of this little extent of reaction deal. And the rest of this is all quite trivial. You do need to I'm going to use this here in a minute. Notice that for the products, there's no negative sign. Why would there be? They're being created. Minus signs for things being destroyed. Plus signs for things being created, and that's just obvious. Again, that's going to matter here in a minute. Anyway, so I hope this is kind of obvious. Now I'm going to start manipulating it into a change in G. Change in G. Okay, so the change in G will be, let's see, how do I want to do this? Let me see here. I think I may have, okay, sorry, I'm just kind of screwing up here, a little addled, because this is just a lot of material. I get a little lost. Okay, this is actually a little bit of a reminder. I'm going to remind you that there are 4 things in this case. Again, I'm just trying to overcomplicate it. Okay, now again, we're at constant temperature and pressure. And don't worry about the partial pressures of A and B dropping as they mix and all that jazz. The total pressure doesn't change. So this just ends up being the sum of the change in chemical potentials, which is in line with what I just covered when I talked about ice melting. Everything just comes down to the change in chemical potential. And again, I just covered that. Okay, so now what I can do is say that dG is, actually I have to admit I'm a little bit perturbed here. Change in G with the extent of reaction. Sorry folks, I just am a little bit, my notes don't make sense. Even though I've been using these for 10 years, I have to admit I'm a tad bit lost why I am, sorry, I'm okay. All right, my bad. I just had a little trouble following my own notes. It's gonna look great on YouTube anyway. No, it's just my formula is right in front of me. It wasn't making sense for a second. And I've done this to myself where I just start writing down my own notes and I don't understand them. Again, that's just, 2 hours straight, it's really kind of a lot. Let me show you how I got confused actually, so maybe it's not a complete wash, am I babbling like an idiot? I'll explain how I got confused and then how I got myself unconfused. Where I got confused there, again, I'm trying to figure out what the change in G is. Okay, this is all hopefully kind of brainless and it's a little new, but it's not that hard. Remember, we covered this in ice melting. Everything's fine. I've defined the changes in N up here. Again, it's like a phenomenological model, but it's totally right. It would not be. What I got a little confused was I saw a change in epsilon, stoichiometric coefficient. That's what I was looking at. In my head, I said, that's the change in N. Where's the chemical potential? I saw this, I didn't see that. It's right there. I'm actually that stupid. Seriously, I just didn't see that. I kept saying, why do I keep equating the change in G with the change in N? That doesn't make sense. Geez, anyway. All right. That's a long day. Okay, very long day. Okay, so now what I want to do is graph this. Baby steps, especially for you graphical people. And I'm going to draw a lot of things like this, like a square box from now on, because it kind of represents that there's a beginning and an end. And just want to point out, let's see, that a lot of things work like this. I don't mean to imply that this is 0 or anything, it's just whatever. Anyway, so the slope is, of course, the change in G. I'm just using, again, first week of calculus. That's the change in G with respect to the extent of reaction. And notice that, let's see, if I bring this down here, remember how I can juggle partials? I've been doing it for a long time. If I do this, I have to recognize that this is actually something I've been doing for a long time. This is actually the change in chemical potential, and let me make it more familiar to you. Change reaction, G per mole, and of course I'll be at standard state. Okay, so again, this ice melts. I've inserted my definition of the change in mass from here. And I know I'm a little overwhelmed myself. Anyway, I recognize if I bring this down here, I recognize this is just the net change in the chemical potential. And don't forget that G per mole is chemical potential. Now, the way I would, so don't worry so much about this. What I like about this is that I know actually how to calculate this. What I would do is I would try to, I would use the formation G's for everything. As long as I consistently do that, it will work. And I would get the products times their stoichiometric coefficient, and I would subtract the reactants times their stoichiometric coefficient. Have you ever done that before? Ever done anything like that before? No? Really? In high school, in general chemistry, you took the numbers in the table in the back of the book, and you got the products minus reactants, of course, weighted by their stoichiometric coefficient. This is a high school problem. Right here. Okay, here's the funny thing about this. So you've done this. You actually know how to do this. You've done it since you were 18. Okay, now, this is where it gets kind of funky. This is basically the thing you did in high school. And if it was negative, the reaction was spontaneous, and if not, it wasn't, right? But what I'm telling you now is that it slowly changes as the reaction goes forward. And what can happen is if the change in G with respect to the extent of reaction is 0, right here, what happens to the reaction? Stops. Yeah, it'll stop. Right, there's no, and not because the extent of reaction has, sorry, let me make sure that that's clear. Not because the reaction wants to stop, well, I guess it does. In other words, for this to be 0, that thing on top has to be 0. But just from a pure mathematical sense, either the change in epsilon is infinity, which makes no sense at all, especially because it only goes from 0 to 1. That's not happening. The change in G is 0 for this to be true. And if there's no change in G, why would the reaction go, right? If the Gibbs energy doesn't change, again, at constant temperature and pressure, there's no reason for the reaction to go forward, so it stops. Okay, so again, high school, products minus reactants G's. What you were describing right here. You were right here. This is the start of the reaction. What you were not shown was how to figure out how that changes, how those chemical potentials change as the reaction goes forward. Because as they do, that change might actually become 0, in which case it stops. And the reaction does not go to completion. Let me explain that in a whole other way, but it's exactly equal. What's going to happen is that the product's chemical potential, being positive in driving this thing, will actually lower. And the products' chemical potential are too low compared to the reactants, but they're going to rise. The product's chemical potential rises, reactants will drop such that this change is 0, and I'm describing that right here. By the way, the reason that's going to happen is because of mixing. Remember, I was just saying that initially, the fact that you're mixing as A and B mix, and then they mix more with C as they make C, this is good, but eventually, A and B start to completely disappear, and that I would call demixing, especially you'll be left with pure C, and that's bad, that's demixing. Demixing is bad, and that's why the reaction may not go to completion. Okay, now let me go back to equations, and then I'll actually end with a graph. And this does get a little bit, I'm just gonna, it's going to be like this. It's just going to be thing, and then the end will actually be something that's a little bit compact, not terribly compact, but digestible. I guess I would put it that way. But to get there, I have to write down a whole bunch of steps. And it's all just algebra. All algebra, no calculus. So let me just do that. And this is how I tend to differ than other folks, because I'm actually getting a lot of emails from Texas, apparently, about how their classes, they're calling me actually, hello, and they're telling me that people are, what other faculty are doing is not explaining anything, they're just giving the end result. I'm doing the derivation so that I guess if I just gave you the end result and then gave you questions on the end result, you could just do it, and then if you do it right, you get an A. But I think it's ridiculous to not show you where this stuff comes from, because then you really get it, instead of, get it versus accept it, right? I don't like accept it, I like getting it. Okay, so, God, what am I doing? Okay, now let's talk about chemical potential of A, which will be the G of A over the moles of A, which will be the number of the table at the back of the book. And I'll do all this per mole. I have to do per mole because I divided by the number of moles. And I have to take into account the mixing. Okay. Now, again, here's the thing. A is a reactant, and its chemical potential is products minus reactants. Chemical potential is high, right? What's going to modulate its contribution is this, right? The mole fraction will change in the course of the reaction. And B and C and D likewise. And they're going to change again by this factor here. And it may change such that that we have this situation here where there's no more driving force. So this is what I'm getting to. Okay, and now what I got to do is subtract C and D minus A and B. Here, let me write down the whole thing. Reaction 3 per mole. Okay, so what it comes down to is I'm gonna take C and D minus. Why don't I write that down? C plus D minus A minus B. You don't need to write that down. Here's the thing you do need to know. And again, in a very compact mathematical, and I'm only doing an example of 4 things. That could be more or less, obviously. Stoichiometric coefficient, technically the number of the table in the back of the book. High school, right here. Here's college, right here. Sorry, RT, sorry, my bad. RT comes out front. Notice that the factor of N is gone because I have factored it out when I did when I divided by the moles to get chemical potentials. It's not a big deal. If you forget that, I won't count off. Anyway, okay, so numbers in the tables up the back of the book. High school, Hess's Law. Okay, high school, Hess's Law. That's where we stopped when you were 18, and this is the bit you get now, which is entropy. This is the entropy of mixing, and it changes the result. This is a thing that may stop a reaction from going to completion. Notice that it's energy because it got T delta S, right? Who cares about R? It just makes the unit work. It's T delta S. See? It's almost like delta H, T delta S. It kind of looks like that. That's not quite right, but anyway. Okay, now I'm going to do this term, and I actually need a whole other board. This is going to take a couple of steps. sorry, I'm not using the board super well. I hope you don't get lost in your own notes about this. Let me do this. The first term I don't need to do. The second term, I'm going to simplify it, and just so you don't get lost, let me write down that the RT sum of I to 4 stoichiometric coefficient, natural log of the. Okay, what I'm going to do is I'm going to simplify this term, but it's kind of long. Okay, so what you get is RT, and I'm going to just factor this. This is, okay, so I'm doing the A, then I'm going to do B. Remember, this is all entropy. That's why I know that, because I see the natural logs. So you can see why this is kind of painful, because I'm just writing the same thing over and over again. And you don't really need to use this. Let me get rid of this. You don't need to use what I'm showing. This is just the derivation to the end result. But again, I just want you to see where it comes from. And OCD means I don't forget the, there we go. Okay, now this gets simplified. You're actually, by the way, you're going to start recognizing this here in a second. Ln chi sub A to the minus stoichiometric coefficient plus Ln chi B to its negative stoichiometric coefficient. And remember that a number to the minus another number is technically 1 over that number. Okay, the products are positive, so that means that they cannot get flipped. OCD, I gotta remember that. There we go. And now I've got this, so you hopefully can see why this is really kind of painful. RT ln. So ln A plus ln B is ln A plus B. Again, if you get confused, just plug some numbers in your calculator. So I'm going to write all this jazz again. It's just that I don't have a bunch of natural logs anymore. And this still, I bet this doesn't look familiar to you very well. Here in 1 second, I'm almost done. I told you this really kind of blows. Okay. All right, now this is the part that looks familiar. Okay, now, again, I'm really sorry that, remember that I'm working on this, but I'm only working on that right-hand side because it's just, it's all over the place. Tell you what, yep. Here's how I can make this easier. Trying to make this easier. What am I doing? Okay, let me, so ultimately, this is what we want. This is delta G of the reaction. And this is still, I'm going to put this in terms of the Hess's law. This is the Hess's law component plus RT ln. Hopefully now this is going to look familiar. RT ln, mole fraction of C, stoichiometric coefficient of C. I've got products over reactants. Right? That's because of the negativity of the reactants' stoichiometric coefficients. God, I told you this was painful. I'm trying to make this as easy as possible. I know you believe that, but this is the best I can do. Does this look familiar? Delta G is delta G naught plus RT ln. Okay? Yeah, I heard a couple of you. Delta G naught plus RT ln K. Right, you've had this before. This is your something coefficient. Your, remember? Equilibrium, your equilibrium coefficient. RT ln K. You had this. It was probably 4 years ago and 5 for high school. But yeah, when you were taught this before, unfortunately this is one of those times I have to correct a mistake. You learned this as a ratio of concentrations. Right, remember that? Concentration of products over reactants? That was not true. That was badly incorrect. We gave you that. We gave you that to because you just weren't ready for the real thing. Right? We weren't ready to give you the actual equation because then we'd have to derive it. You just saw me flounder like a fish, even though I'm actually kind of got it together today. You just saw me flounder like a fish. The reason that, and I'm not going to write this down because I don't want to confuse you. The reason that, I mean, I hope you believe the derivation I just showed you, and clearly this is not what we fed you in high school, and I'm telling you what we fed you in high school is wrong. One way to have known that is, let's say you had A goes to, let's say that you had two products in one reactant, like a decomposition reaction. A goes to B and C. You would have had natural log of moles over moles. You would have had natural log of a unit. Is that wrong? Right, you cannot take natural logs of something with units. Or we covered that at the very beginning. That doesn't make sense. You can't have e to a joule. You cannot take natural log of joules. You cannot take natural log of something with moles. I mean, you can write it down. You're just a moron. That cannot correspond to a physical reality because it just, again, you can't. If you recall, the reason is because you can write natural log as a series, as a Taylor series. 1 plus x squared plus x cubed. And if your argument had units, you've got an equation with no units plus units squared plus units cubed, yada, yada, yada. And that can never happen. It doesn't make physical sense. So this is the actual RTLNK. Now, let me foreshadow a little bit. Delta G. So this is delta G reaction, I guess that's per mole as well, I guess so. But anyway, okay, now here, let me foreshadow a bit. Remember I told you that you're going to calculate the equilibrium concentrations of reactions? Now, when you are talking about A and B reacting to C and D, at the beginning, you know what delta G is. It's right here, because this is going to be 0, because nothing's mixed yet. So the numbers in the tables in the back of the book, the thing you did in high school, tells you initially whether the reaction goes or not, whether the reaction is spontaneous. But that's all it did. Okay, as the reaction kicks in, this part starts to come alive. And when the reaction is over, what's this?
0.
Right. So you see, you can figure out what the reaction extent is because when this is 0, all you have to do is figure out what these different mole fractions are. RT, ln of those mole fractions equals the Hess's law. That's actually what you're going to do. And that sounds probably a little complicated. It is. And I'm going to show you, I think, on Monday how to do it. But let me give you a little bit of a hint. And I'm going to show you. I'm going to show you almost how to do it right now with an example. And then Monday I'll show you how to actually do it so you can do number 8. But what I want to say about that is, do you remember on the first homework or the second homework where I had this crazy long equation? It was like 0.016 is equal to something, natural log of alpha. Do you remember that? You remember that? It had you solve for alpha? Yeah, it's on your next homework. That equation is on your next homework. That's why I had you do it, so you could hack this when the time came, which is now. I've actually been manipulating you in all kinds of ways that you don't know. You've actually done problems that will be on the last problem set of next semester. I've actually done that. You didn't even know it yet. You'll know it in a couple of months. Okay, so anyway, let me show you. So I'm playing it up quite a bit. Let me show you how that works with a simple example, because I promise I'm not going to do something as complicated as A, B, C, D, because that's a hell of a lot. I'm going to stick with like A goes to B. I just wanted to show you how complicated this could actually get, but I don't need you to do a very complicated example to show me that you know how this works. A goes to B is just fine. If you can do A goes to B, I believe you can do something more complex. It's just a matter of do you screw up your calculator or not, and I don't like to test that. Okay, so let me do the delta G of the reaction. Anyway, I guess this is, I'll be at standard state. I get my symbology a little confused. Okay, it's the difference in chemical potential, and it will be the number of the table in the back of the book, which is the formation delta G of whatever B is. Now, this is the part that allows for mixing with so in this case, again, if delta G, the high school, is negative, that's great. That means A wants to form B. Now, you've known that since high school. The crazy thing is that as A forms B, it mixes, but as B is formed in more and more excess, it's demixing, and that's bad. This is the bad part. This is the part that may stop the reaction from working. I'm actually going to go a little bit backward here. I'm going to get rid of that mole fraction. I'm going to put it back in the form of a pressure, because this is how you're going to do this practically. Okay, now we have to subtract out the A part. Again, the number in the table in the back of the book, the formation G of whatever A happens to be, R, T, L, N. Now, so I'm sorry to have done this. This is why this is kind of a little complicated. Again, the thing I've done here is I've decided to not use mole fraction to represent this entropy part, because it's going to actually make the question a little bit easier. And therefore, this is equal to the high school part plus RT ln. So notice that I'm not going to do the algebra. That if you B minus A, products minus reactants, number in the table at the back of the book, high school, college level right here, factor the RT, and then you can put these two together such that you get a natural log of PB over PA. I'm trusting that you are cognizant of natural log A plus natural log of B to do that, right? So I'm praying that's the case. Okay, let's call this part number 1 and this part number 2. And I'm actually just covering what I just said, but I'm going to do it graphically, because why not? Okay, so let me cover part 1. And I will do this extent of the reaction deal, which again is what I defined before, but I deleted it. Just not reacted, fully reacted. And let's assume that this reaction has a negative delta G, and that means that the G per mole of B is less than A. Otherwise, why would I be doing this to begin with? Sorry, I kind of have a room here. Okay, so again, A will form B because its G is too high. That's per mole, so it's chemical potential. This is part 1. And then what you add to that is part 2, which is RT ln PB over PA. And again, this is going to be as a function of the extent of reaction. And I'm not going to put in numbers. I'm just going to point out that basically it bows downward. It bows downward because of, remember, this is the entropy part. This is the mixing part. So, table in the back of the book plus college mixing part equals the total. What does that total look like? Just doing such a bang-up job of using the board today. This. So I'm working down. Sorry, I'm just trying to use one board when I'm doing a derivation, so I'm not jumping around like an idiot because it's annoying. Let me add the two together. So this is the total. And again, it slopes downward because of the guy on top, but it bows and may bow back up. Sorry, this looks kind of like this weird reflection, my bad. I'm a little OCD about making this look just right. So again, the reaction goes down because of the number in the table in the back of the book. but it eventually droops off, and it may actually not go all the way, and that's actually the mixing. That's the A holding back, forming B, because if it does so to completion, nothing is mixed, because it's pure B, and that's not mixed, and it doesn't want to do that. Okay, so, and that's why things don't react to completion, right? So that was the kind of funny thing. I remember learning when I was in high school chemistry and freshman chemistry, when we were learning about delta G's and they were negative, my first thought was, well, if it's negative, then the reaction goes and therefore goes to completion. If it's positive, it doesn't go at all. And that's completely wrong, right? And for those of you who do any synthesis, you know that your reaction is almost never 100%, and now you see why. Now, here's another little funny factoid. Because of exactly this, if the delta G is positive, let me give some, so that hopefully is for you visual people. That's just a graphical representation of everything I've just been saying. I just hope it kind of solidifies it. Let me give alternative examples of what I just said. Let's say that the high school delta G is positive. In other words, the reaction doesn't go. That's not true. The reaction does go, just not very far. Now in that case, your contribution of 1 is bad. So this doesn't react, this reacts fully. Numbers in the table at the back of the book say no, forget it. But the mixing part, here I'll just draw the net results. 1 plus 2. The mixing part says that actually you'll react, just not very far. So again, A forming B is not going to happen. You already don't think it's going to happen from the number in the table at the back of the books, because B's chemical potential, the number in the table at the back of the book, is too high. That's bad. But A will form B to a small extent just for the entropy of mixing, just to be able to do that. Okay, that's one example. Let me give you another example. Why do things react to completion? I have done reactions that spark methane with oxygen. That reaction will go to completion. In that case, here I have to be very extreme. All right, in that case, the high school part, the G per mole of the products is so freaking low. This is, oh, sorry, I'm trying to be consistent with what I did before. This is 1. When you do the plus 2, which is the one that matters, it doesn't matter, right? You see my point? Okay, again, the high school thing is a dotted line. I'm dotting it because it doesn't, that is not really what's large and in charge, it's just a part. But if it's a big part, it actually will overwhelm the entropy, number 2 part. It will overwhelm it, and this is a reaction that does go to completion. So there you go. Let me give you another way to think about this, by the way, especially for reactions that go to completion. And this is prepping you for 344. But so again, why do things go to completion? Let me give you the entropic, another way of doing this with entropy. What I'm going to do is I'm going to make a weird graph of energy and population. Now, actually, if you want to just absorb and not write this down, that's okay. I'm not going to test you on this. This is an entropic explanation of why reactions will occur even if they're not favored by the number in the table at the back of the book. Okay, so what can happen if A goes to B? Let me give you an example of why a reaction normally wouldn't want to go. A has lower energy than B, and these are quantum energy levels. I told you I'm prepping you for 344. B has quantum energy levels that are higher. Okay, so in this case, what happens is the population wants to live at these energy rungs. They want to live down here. Occasionally heat causes them to move up, and then they move back down, right? Heat flows and whatnot. But this is a low energy quantum state, and there's a lot of population here. A will not form B, or it will do so very, 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 very poorly, right? I know this graph is kind of weird, but you'll get used to it. Okay, so again, lower energy and more places to be. And that's the entropy part. Lower energy is energy. These rungs are places to be. That's the entropy. This reaction does not occur. But now let me change the quantum mechanics to introduce more energy, which is the same as more microstates, which is the same as entropy. Let's do this. Now what I'm doing again is I'm increasing the entropy of B. I'm doing that by giving it more microstates, which in the language of quantum mechanics that you are very close to being in, is more states. More states is more entropy. Entropy drives reactions. Okay. This is a reaction that will occur. Because what happens is, as heat occasionally takes A into these higher levels, it wanders into B, it wanders into the B place, and it gets lost. So this reaction actually does go because when A does wander into B space, there's so many places to be, that means higher entropy, that it will actually choose to stay because it simply is improbable that it finds a ways out. That's a reaction that the number of the table at the back of the book says does not happen. That actually does, and this is why. Sorry I've gone over.